Christian, is this the right location? Okay, good. Thank you very much for the introduction. So this is the second peridynamic talk of this workshop. And also last year we also gave a couple of presentations as well. So today basically I will talk about how we can come up with beam and plate formulations in peridynamics, and we will mainly focus on two different ones, which is the Timoshenko beam formulation and medium plate formulation. I will also briefly explain how we can come up with the peridynamic formulation for Euler beams. Since some of you may not be that much familiar with peridynamics, I will just make a small introduction, and then I will move on how we can derive the peridynamic equations for the beams and plates. So basically, as Selda was explaining, peridynamics is, according to us, a new continuum mechanism formulation, and according to Francesco, actually it's an old one because Piola invented peridynamics before. So it may be a good thing in one sense, because if you have any complaints, we can blame Piola. But if you have something good to say, so please you can just let us know. So basically, peridynamics is a new non-local continuum mechanism formulation. Why we are saying it's new? Because it is using integral equations as opposed to partial differential equations. And probably, as also Francesco highlighted earlier, although there are similar formulations earlier, peridynamics is especially good for predicting failure. So that's, I think, kind of the new feature of peridynamics. So it is very suitable to predict crack initiations and propagations. And also, one nice thing about peridynamics is, if you compare against classical approaches, the way that we define failure is pretty simple with respect to, as I said, the classical fracture approaches. So the way that we prescribe the crack growth law is very simple. And also, we don't treat cracks as special objects of the formulation. They are just part of it. So they are just natural part of the formulation. So any number of cracks can occur and they can easily interact with each other. And also we can easily define interfaces. Again, this is a good feature that some existing approaches cannot handle. And also, although this is an integral formulation, basically to solve these equations we normally use meshless approach that Selda was presenting earlier. And once we discretize our integral equations, it turns out that these equations, they look very similar to molecular dynamics equations. Although it's a continuum mechanism formulation, those equations are very similar, they look very similar. So we are hoping that it may be an easy way to couple molecular dynamics and this continuum mechanics formulation, so that we can use it for multi-scale type of applications. So just as I said, I would like to just give a brief introduction on peridynamics in case you missed Selda's talk. So basically, we are now using a new type of equation of motion with respect to the Cauchy's equation of motion. Although actually many of the terms are the same, we are just replacing the term which has special derivatives, because these terms can cause problems, especially if we have discontinuities, especially in displacements. So what we do is, in those cases, we would like now to replace these derivatives with an integration. So this term now doesn't have any derivative in there, so it is always valid, even if we have a discontinuity in the structure or not. So that's kind of the advantage of peridynamics. And another difference between peridynamics and Cauchy's formulation is the way that material points are interacting with each other. So Cauchy's formulation is limited to nearest neighbors, but in peridynamics, all material points can interact with each other. And the way that we are defining these interactions is by introducing these peridynamic bounds. And after defining these bounds, basically we are just defining these forces, interaction forces, and this is the force that this material point is exerting on this, and this is the force that this material point is exerting on this. Like as all other formulations, basically we are just using Newton's second law to find the motion of a material point, and this time we are just summing up, or we are just integrating all the forces acting on a material point that we are interested in to find out this motion. So although the theory is flexible in a sense that we can take into account all interactions inside the body, so all metal points can interact with each other. But the thing is, since we normally do a numerical calculation, if we take into account all these interactions, it will be computationally very expensive. So what we are then saying is, why don't we limit these interactions to a particular region that we call a horizon? So basically, we are just assuming that the material points are only interacting within this domain, and outside of that domain, there is no interaction. And how about the peridynamic force? This just depends on the material. But for a very simple case, if we assume the material is elastic and isotropic, so in that particular case, basically this interaction can be described like a spring force. But what we do is we just don't represent in a classical manner, so by just multiplying spring stiffness times the change in length of the spring, we just introduce a new constant that we call a bond constant times the stretch. So stretch is basically the change in distance between two material points after the deformation, and we just divide the change with respect to the original distance between two material points. How about our bond constant? Actually, you can assume that this bond constant is kind of our material parameter in this new formulation. But the good news is basically we can always find out these constants in terms of the constants of the classical formulation. So if you know, for example, Young's modulus of a particle material, we can calculate our parameter. Since I just mentioned that this formulation is really good for predicting failure, we need to somehow also reflect this inside the formulation. And it is pretty straightforward to do this. So what we do is, of course, we need to consider what type of material that we are dealing with. But as a simple example for a brittle material, what we are assuming is if the stretch between 2 points exceeds a critical stretch value, that we call critical stretch, then we just assume that the force just drops to 0. So in other words, these two material points, they don't talk to each other anymore. So how do we find this critical value? Again, that's something that we can relate to classical parameters, classical fracture parameter. So we can just find out this parameter in terms of fracture toughness. So if we know the fracture toughness of the material, we can calculate this parameter. So, after this basic introduction, this particle talk, as I mentioned to you earlier, is on plate and beam formulation of peridynamics. And as I mentioned earlier, it's a pretty suitable technique to predict failure. But when we try to handle three-dimensional geometries, is in finite element analysis, it's very computationally expensive. And also, when you move to 3 dimensions, you start having too many interactions and so on. As I say, it's becoming pretty expensive. Of course, we can use parallel programming so that we can just discretize, or we can divide our domain into multiple pieces, and each piece can be handled by a particular processor so that we can easily reduce the computation time. And the formulation is very suitable for this. But of course, especially in some cases, if you want to analyze very large and detailed structures, like a ship structure as in here, it's better to utilize simplified formulations, as we normally do in finite element method, for instance. So basically, our goal is to come up with peridynamic formulation for beams and plates, because the formulation that I just showed you, it is mainly for a case that each material point can only have some type of a translation. But as you know, when we come up with beam and plate formulations, we need to also take into account, for example, rotations and so on. So we need to modify the formulation. The first formulation that I will present today is the Timoshenko beam formulation. So basically, this formulation is good for both thin and thick beams. And before I start, so let me just provide you some parameters that I'm going to present later on, so that we can follow the formulation in a simple manner. So basically this is our beam in the original configuration, and we have these two material points K and J, and after some time the beam is deformed, as you can see in here. So these two material points, they move to their new locations. And also what we know is in Timoshenko beams, the lines which are initially perpendicular to this neutral axis, they don't stay perpendicular to each other. So what we now have, we have a shear deformation. And also for this Timoshenko beam formulation, each material point has 2 degrees of freedom. One of them is the transverse deflection W, and the other one is this phi, which is the rotation of the cross section at these two locations, at the location of a particular material point. So in peridynamics, basically, the way that we define these transverse shear angles is a little bit different with respect to the classical formulation, as you will see now, but also in some sense it's also very similar as well. So since in Timoshenko beams, basically the derivative of these transverse deflections, they are not exactly equal to the rotation of the cross section. Basically the difference will provide us the shear angle, and actually that's how we define in peridynamics as well. But the way that we do is we don't use derivatives, because we don't like derivatives in peridynamic formulation. Instead, angle in peridynamics for these two material points that I am interested with, which one? The first one is the J material point J, and the other one is material point K, and these are the ones which are interacting with each other. But of course you can always change this J to some other material point, as long as it is inside of the horizon of material point K. So as I was mentioning, basically we can define the shear angle as the change in displacement or relative displacement between these two material points, and we just need to find the ratio with respect to the distance between them. And if we just compare this particular value with respect to the rotation, we can find out basically the shear angle of the material point J, and we can do the same calculation for the K as well. But as I was mentioning earlier, when we talk about peridynamics, we are talking about bonds. Okay, so we need to somehow can find out an equivalent quantity which can describe these two values. So what we do is we are just taking the average. So basically we just define this phi kj. So this is kind of the shear angle of the bond between K and J, and this is calculated as I said based on the average of these two shear angles. And another important parameter for bending is basically curvature. And we can define the curvature again without using any derivative, but by looking at the difference between the rotations of material point J and material point K. Again, if we divide the difference between these two rotations with respect to the distance between them, basically we can calculate the curvature value of the bond between K and J in peridynamics. So you can actually also guess easily, the corresponding value in classical quantum mechanics. But in all cases, as I said, in classical sense we use derivatives, but this time instead of using derivatives we look at the differences, finite differences. So after introducing these important parameters that we are going to use in our formulation, now I will try to present how we can obtain the equation of motion in peridynamics. And as we normally do in mechanics, we can utilize Lagrange equation. So if we can calculate the total kinetic energy of the system and the total potential energy of the system, and by using these two, basically we can come up with our Lagrangian definition. And then once we substitute this Lagrangian parameter into our equation, it can provide us our equation of motions. And that's what we did also for peridynamics as well. And in this case, this Q is basically our degree of freedom. So as I mentioned earlier, for Timoshenko beams, we have 2 degrees of freedom per node, which is the transverse deflection and the rotation. So here, what we do is we are just summing up all the kinetic energies of all material points inside the system. Since our metal points are very small, so we have infinite number of metal points, so we have this infinite summation here. So we are just summing up all the energy, kinetic energy of all the metal points inside the body or inside our beam. So we have one energy coming from the transverse deflection and the other one is due to rotation. And when we come to potential energy, well, there are some terms which are kind of specific to peridynamics, but also, as you will see, there are kind of correspondence in, for example, in molecular dynamics as well. So what we do is we are defining something called a potential. So this is kind of a similar potential between atoms, but as I said, this is a quantum mechanics formulation, so we, instead of atoms, we are using metal points. So basically these potentials are describing how the metal points, in this case K and J, are interacting with each other, how they are influencing against each other. And one thing that we need to keep in mind is, the influence of one metal point on another may be different with respect to the influence of one metal point to the other one. So they don't have to be the same. This omega kj and omega jk, they don't have to be the same. So then what we do is, since as I said we are dealing with bonds, we just average them all. So if we to calculate the potential of a particular interaction, basically, we just need to take the average of these two quantities. So, and as you know, from the potentials, when we take the derivative, we can calculate the forces. So that's why basically these quantities are just here, just to describe the energy of the interaction between these two metal points. And also what we did is, since in beams there are two different scenarios, one of them is bending, the other one is the shear deformation, we just decompose these energies into two. So the ones that with tilde had tilde operator here, they are corresponding to the energy describing the bending behavior, and as you see they depend on the curvature. And the other energy is reflecting or representing the shear shear energy, and they depend on this shear angle. And also in our potential energy expression, we also have the energy due to external forces, and these two guys are representing those. So as I told you, once we actually use these two different parameters, once we use the Lagrange equation, we can calculate our equation of motion, and that's what we are doing here. So we just use these two equations, which will provide us two equations of motion in the formulation. And if we investigate some of these expressions, what we can realize is actually some of these parameters are describing a force. So the forces with this head parameter, they are describing the force related to shear deformation, and the forces related to tilde, they are describing the force related to bending. And so we can write the equation of motion, these two equations of motions here. So then what we did in this particle formation, so once we identified the forces related to the shear and the bending, we just defined them in terms of a bond constant times shear angle for the shear force, and for the force related to bending, we just come up with another meter parameter or bond constant, the CB times the curvature in between. So once we use them, we can obtain the equation of motion of Timoshenko beam formulation in peridynamic form. Okay, so these are the two equations that we can use to represent a Timoshenko beam. And as I told you before, we don't take into account all the interactions. So once we limit the interaction to the horizon, and once we convert all these infinite summations or all our summations to an integration, basically they will take this particular form. So now basically these are the peridynamic equations representing a Timoshenko beam, but with a horizon parameter. Okay, once now we have the equations, but which is missing now is these bond constants. So we need to find out what they are. And the way that we do is, in a limiting case, basically peridynamics should converge to classical quantum mechanics. And then that limiting case is basically when the horizon is converging to zero. So if that is the case, actually we can write down or express our transverse deflection and rotations in terms of the displacements of the neighboring points. So once we express all these guys, and once we actually include them, or once we substitute these parameters inside our equations, we can simplify our equation, and they will take these two forms. And if you actually compare these guys against the classical equations, you will see that they have the same form. So by just now equating these two equations, which is coming from peridynamics and classical quantum mechanics, basically you can find out the relationship between bound constants for bending and shear in terms of the shear modulus, elastic modulus, and moment of inertia, and the cross-sectional area. Okay? So we don't need to do any new experiments, but instead, by using these relationships, we can calculate our parameters. So I will now show you very simple examples. In this particular case, I have this cantilever beam, I have this bending acting at the right edge. So here you can see that our rotations and transverse deflection, they match very well against analytical solution. This is, if you have a transverse load, again we have a very good match between classical and peridynamic formulations. And the next thing that we did is we also looked at, we were trying to find out the dispersion relationships for the Timoshenko beam, just to see that how if we can use peridynamics to describe different type of materials. And in this particular case, as we normally do, we just assume that the deflection and the rotation in this particular form, that we have this wave number and then we have this frequency. So once you substitute these guys into our equation of motion, it will provide us this wave dispersion relationship. And after that, basically you can calculate our frequencies and also phase speeds. And if you compare now the classical, the wave frequency from the classical formulation and peridynamics, as you see that for long waves, basically classical and peridynamics, they are the same. But once we have shorter and shorter waves, the peridynamic wave frequency or peridynamic dispersion relationships, they are diverging from the classical equations. So this kind of gives us an indication that peridynamics can also be a good tool to represent materials that maybe classical quantum mechanics cannot capture. So we can apply the same logic to describe a mid-limb plate formulation. This is more or less exactly the same. Okay, the kinematics also is very much the same. So we can again look at two material points, and each material point can have this transverse deflection and rotation. But now, since we are talking about a plate, we have a new basically dimension. So what we need to do is we need to decompose our basically rotations into two different parameters, which one of them is along x direction and the other one is along y direction, or the rotation along x direction and the rotation around the y direction. So once we do, once we follow exactly the same steps that I was describing earlier, so once we use the again Lagrange equation, we can obtain our equation of motion as I mentioned to you earlier. So these are basically the three equations this time that we have, corresponding to 3 degrees of freedom per node. So we have transverse deflection and 2 rotations. And then again we have these two parameters CS and CB. To find their expressions, again we can just assume that for a limiting case, our peridynamic equations should convert to the classical equations, and that's what we have now. So once we do that particular simplification, our equations, they have the same form as the classical formulations. So once we equate these two equations, we can again find out the relationship between our peridynamic constants and the constant that we have in classical quantum mechanics. This time, what we did is basically for plates, we also tried to consider damage, since peridynamics is pretty suitable for damage. And the way that we do is, since we now have two different forces, one of them is responsible for bending and the other one is responsible for shear, and each of them may represent a different story. So from a fracture point of view, as you know, we don't have just one fracture scenario. We have 3 different modes. So we have opening mode and we have shear mode. So what we said is, this bending mode should create opening of a particular crack, and this shear basically force should create mode 3 type of fracture pattern. So, and also when you also think about the meaning of critical energy release rate, basically this is the energy that we need to input to the system so that we can create this unit crack surface. So if you can calculate the energy of all interactions passing through this crack surface, if you break them all, if you calculate the entire energy, and if you equate them to G1C, which is the critical energy release rate for mode 1, and the G3C for the energy for the mode 3, basically we can calculate the critical curvature and critical curvature and the critical shear angle which are the limits that we can break our interactions. So again, we just validated our formulation by just considering some simple examples. As you see, peridynamic and classical or finite element formulations solutions are there on top of each other, and also we just consider a very simple case that we apply bending moment. We have a crack in here, and once we start increasing our load, basically our crack starts to propagate. So this can just give you an idea that actually our formulation can also predict failure. And again, we just look at the dispersion relationships. At this time, instead of 2, we have 3 degrees of freedom per node. So this is basically our dispersion relation that we need to obtain from this determinant. And these are basically the frequency variations. And as you see, again, we have a deviation with respect to the classical formulations for the first three modes. And again, for the phase speed, once we increase the wave number, we have a deviation between peridynamic results and classical results. And you can apply the same logic for Euler beams as well. The good thing about Euler is basically we can reduce the number of degrees of freedom from 2 to 1 so that you can reduce the computational time. And you can just follow the same steps that I showed you earlier. And again, you can obtain your equations. And as you see here, we just again consider some simple examples, and we obtain very good match between peridynamic results and analytical solutions. So, as a final remark, today I was just trying to show you how we can actually obtain peridynamic, Timoshenko, Midland plate, and Euler beam formulations so that we can reduce the computational time in our simulations, and also at the same time I provide you the dispersion relationships, which kind of gives us an idea that peridynamic results are different with respect to classical dispersion relationships for a certain range, so which can help us to maybe model materials which we cannot consider classically. And before I stop, I just want to also give, make a small announcement. For some reason, this year everybody is organizing something, so we are organizing as well. So this is a conference on computation mechanics, which will held in Glasgow in September, from 10 to 12 September. And I just want to mention that this is not a peridynamics conference, it's a general computation mechanics of materials conference. And we have pretty, distinguished keynote speakers. So I'm hoping that, at least some of you will can participate in this particular workshop. We will be very happy to see you there. And we will also have some flyers that we will also distribute after my talk. And with that one, thank you very much for your attention.
Possibly one very short question?
I have a very short question. It seems to me that you can also describe the finite deformations for a beam. Why not? I did not consider it nonlinear deformation.
Right, of course, actually, as you are saying, this one is just limited for small deformations, but after this formulation, the next step is, as you are saying, it's easy to extend to nonlinear deformations. So it's very straightforward.
Yes, because it's more interesting and more...
Yes, actually we already did that, but in a numerical manner. So it's very straightforward, as you are saying. Thank you very much for the comment.
Okay, I think we are running out of time.
Thank you again.
Thank you very much.